Hey folks, so this week we get to talk about causal inference, and in the process we'll also talk some about get some more practice with our regressions, and specifically we'll do some multiple regressions, quite a bit of it, and so we get some practice with that. Now before I get started, just a quick little administrative note. As you can see, I've been working on this PyMC3 RViz cheat sheet for you guys, and I've cleaned it up some. You should already have the link, but I've also included it in the description of this video so that way you can access it. We'll keep adding to it throughout the semester. And so by the end, you should be able to have a lot of different examples on data sets and using the techniques in PyMC3 and RViz. And also on top of that, you also get some of the modeling techniques that we cover in class. So that way you can always use this whenever you just need a refresher or trying to copy some code to then manipulate and modify. All right. So to start with, let's go back to a little high level again and talk about why are we even doing this modeling to begin with. So there's two main goals with doing modeling. All right. The first one is prediction. Right. So a clear goal is that we have a bunch of inputs and we want to predict the outputs, right? So you have some x's and then you have some y's, and then I tell you, okay, well, here are some new x values, and I don't know what the y's are. Can you predict it for me? And these days, of course, that's all the rage with things like with neural networks and the like, because you can do things like, okay, here are some English language text, and here's some Chinese, the translation of it. Now here's some more English text. What do you predict the Chinese translation will be? And that's how Google Translate works. Well, roughly. I mean, it has to do this task. And then similarly, okay, here's a picture. Is it a cat? You know, and in general, like I said, machine learning is kind of taken over with this, but machine learning does have some limitations, which is mainly that when you hand it a bunch of data, it's usually very good at trying at being able to predict within the range of data that it sees. Now, of course, once you move into a lot of really high dimensions, this can be a really difficult task, and it really excels at that. But as soon as you start moving outside the range of data that it's seen, if you suddenly start asking it, what about these x's over here? Uh, it has a hard time doing it. And let's be honest, with us as humans, we'd also have a hard time doing this, right? Because if I suddenly label this, say, weight and height, which is some of the data that we've seen before, we might not predict that it's going to be some line that goes through some value above zero. We might say, oh, well, we know the intercept has to be zero for this. And maybe it curves for some of it because you're growing, because this is mainly down here for children and they have different properties, right? There's a lot of extra information that you get once you're given context. And without the context, and you just have the data to work off of, it's pretty hard to make predictions for extrapolating, for outside the range of the data set. And like I said, notoriously difficult for things like neural networks to do, where when we're handed the same data, because we have our context and we know features of what's being measured, we actually can often surpass the neural networks when we're working in extrapolation. And so a lot of the statistical techniques that we're going to be covering in this class can still be useful when you're dealing with trying to make predictions, useful for prediction, when you're doing, well, they're useful in general, but they can even be better than a lot of the machine learning techniques, I should say, when you're dealing with trying to predict stuff outside of the range of data actually observed already. And so an example of this is when you're looking at election forecasts. Every election is somehow unique. And so, for example, in this last one we just had, for example, unemployment and the economy were kind of in dire straits, and still are because of the pandemic, where you had the largest unemployment like in history of the U.S. It was so bad. And so how do you predict the election under those circumstances? Simultaneously, it was okay. Well, the president who's running for re-election has been impeached. That hasn't happened before. So there's a lot of different aspects, and of course, demographics are always changing. Political polarization changes. There's all sorts of things that change, and alignments change every single every election cycle. And so trying to sit there and take, the limited data set that we have that's clearly applicable, we've maybe, if you look back, okay, let's say any election in the last 80 years useful, that's only 20 elections. So how do you take the data from those 20 and somehow formulate a good model for what's going to happen in the next election? You can't fit a neural network on that. And you got to end up embedding some context into it, some sort of information, priors, model for what functional forms things will take, things like that. You actually have to include some information from outside the data. And so this stuff is still very useful no matter what you're trying to do, even when you're trying to do prediction. I think that this is still incredibly valuable stuff. And there's certain parts of prediction that is still dominated by just standard statistics. All right. The second thing is causal analysis. And that's going to be the focus on today's class. And causal analysis is a little bit different. We're not so much trying to say, okay, here's some X's and Y's and now predict it, although that is kind of a byproduct oftentimes, although usually you're willing to sacrifice some of your prediction power, which we'll talk about at the end of class. We'll actually show you a model where the correct model for doing causal analysis is by every metric worse at prediction, but it's actually better for our causal analysis for our purpose. So with causal analysis, what you're trying to do is you have your data, for example, weight and height, and what we want to say is, does weight actually affect height? Does it cause a difference in height? So if we increase our weight, will that change our height? Now we know, no, it doesn't, right? In fact, we know it's probably the opposite, that if you raise your height, if you actually grow taller, then you're likely to have gained weight. Although even there, it's in the process. Even there, that's a little bit iffy too, because there could be certain cases where it's like, okay, you gained height by wearing heavy, taller shoes or something, or in my case, at one point, they had to go in there and do some surgery on my back, and I gained like a good inch there, but no new material. I didn't weigh anymore. Um, so it depends a little bit, but in general, if somebody's growing, they have greater height and they typically gain greater weight because they're taller, and therefore there's just more mass there. All right. And so what we want to be able to do, though, is talk about these relationships. And it's not in the data, right? The data doesn't tell us it by itself, right? We have to impose some of our beliefs and thoughts and models and theories onto the data. And then what we can do is that once we have our theories and models, we can then compare it to the data and see, does the data um, help confirm our theory, or at least is it compatible with our theory, or is it totally incompatible with our theory? And so we'll talk about that in just a moment. All right. So there's two types of theories that we can do. The first is kind of very high level, and it's a statistical model, just a simple statistical model. Statistical. You'll also see these in the econometrics literature. These are typically called reduced form models. And in our book, with statistical rethinking, he calls these geocentric models, oftentimes. Although that's more of a by analogy. If you read the book, it would make perfect sense. All right. And in general, what these are linear regressions, where we don't actually think that the universe works by linear regression, but it's an okay, just trying to fit it as some general linear model. All right. An alternative is to actually have a full-blown theory. This is like having Newton's equations for motion, right? Or for gravitational pull, where you have the elliptical orbits and such. you actually have some full-blown theory that makes really precise predictions. All right, and these are going to be called mechanistic models. Mechanistic. And in the econometrics literature, they call them structural models. All right. And so these models typically have a lot of theory that builds up to a functional form based on the theory. And these are typically much better than these, right? Now, they aren't always, sometimes some behavior is just difficult to capture, right? And actually capture in a nice model. And so a lot of times with what we're doing in economics and microeconomics, it's really difficult sometimes to come up with a theory for how people are going to behave. You can try to say how they should behave rationally, and even that can be really difficult. But lots of times you end up just running statistical or reduced form models also, just to kind of say, well, do they tend to do this? Do they behave into this behavior in this particular way where they increase, say how much they purchase based on, some certain property of the market? You can ask that question just from a statistical point of view, or you can try to build up some theory on why it might be that, for example, when they have more choice, they buy more stuff, right? There are simple theories around that you can try to build up a mathematical formula that makes a prediction. You can test that theory against the data. All right. So in this, for today, we're just going to focus though on the statistical models and how, with a statistical model, we can still try to get out some causal analysis. All right, and some causal implications. All right, and also warn you off about the potential pitfalls when trying to do so. So let's get started. Suppose I have some data here, which is, and by the way, we're going to be doing a lot of analysis, and I just want to state that all the data today is going to be made up by me. So I will simulate all of it, and I'll actually show you the function I use to simulate it, because this way we actually know what the true answer is behind the scenes, and we can just see how the different ways that you analyze the data can lead you astray from what is actually going on. So let's suppose that on the x-axis we got ice cream sales, kind of a classic, and on the y-axis we have crime rate, or I'll just say crime. All right. And it turns out that if you try to do this graph, and we will in just a moment here, you get a positive, and you do like a linear regression, you get a positive correlation. And it looks and it's actually quite strong in the data I gave. But in real life, there really is a positive correlation between the two. Now, we all know that ice cream sales don't create more crime, right? It's not like, okay, if you suddenly start selling more ice cream someday, that's going to lead somehow to more people committing crime. It's not like you eat ice cream and it makes you want to go out there and rob a bank, right? But first, let's look at the data and show that this really is true, at least with the simulated data. But in real life, I'm telling you, it really is also true. And then we'll talk about what's going on and how do you actually get to what's going on causally underneath. Right. So right here, I got my, I already have the file and I already have some of the data set up right here. But here's just some data for the ice cream and the crime, and they're in arbitrary, pretty much arbitrary units here. But first we run this and load in the data. And now if we want to fit this model, what we can do is easy enough. We can say with pm.model as confound m. There's a hint that this is a confounded model. And we'll describe exactly what I mean by confound model in just a moment. So let's try to fit this. So first we got to have our alpha, and we got to put in some sort of prior for this. And I'm going to just leave that blank for right now, because we'll talk about it in a moment. And then we also have one for our slope, and I'll also leave that one blank. And then, of course, we actually have our standard linear model here, where we have that the mu is equal to alpha plus beta times crime, times ice cream. Sorry, ice cream is our x. And then, of course, crime. Oh, and then, of course, we also need our typical sigma here. pm.exponential of sigma, and I'll just set that to be 1 for now. And then crime is equal to, oh, we got to do crime kind of predicted here. I'll just call this C, is pm.normal C, with mu is centered on the mu, and sigma is centered on sigma. Right? And then observed is crime. All right, so this should work. We just have to fill in our alpha and beta priors on the alpha and beta. Now the problem is that first of all, I don't really know anything about ice. Like, how are they even measuring ice cream sales? Is this number of ice creams, number of ice creams per person, or I doubt that. I mean, I don't typically eat 100 ice creams in a day, but it could be ounces. It could be anything. I don't even know what the units are. And same thing for crime. I'll be honest, since I made the data, I can tell you this is completely made up ranges. All right, it's totally that doesn't mean anything. So when you're in this situation, well, what you usually want to do is have something where you can actually have you want the data in some sort of range where you can actually say something about your priors. So when it was with height or weight, it was okay because we could say, oh yeah, we know what a typical person weighs, or we know what the typical relationship between height and weight might be ahead of time. But with this, we don't know anything, right? Now, one thing we could do is go out there and try to learn about the actual data. But once again, context here is king. So if you have some more context, you'll be able to come out with some pretty good priors. All right. But in other cases, and this is what I'll do for most of today, it works just to try to transform the data into a format where we can say something about our priors. And in this case, the way that we can transform this data is to standardize it. All right. And to standardize, what I mean is you subtract by the mean. So we can say ice cream standardized, I'll put an S there, is just equal to ice cream minus the mean of all the ice cream data. And then divided by the standard deviation. So now when you do this, let me first just print out what it looks like. It transforms this data here into this data here. And this data has mean of 0 and standard deviation of 1 by definition, by construction. And in general, the way you can interpret a value like minus 1.18 is that it is 1.18 standard deviations below the mean. All right. And up here, this one, let's see, there should be some equally above the mean, thereabouts. So there's one that's 3.266 standard deviations above the mean. All right. And so what we can do is if we standardize this data, it turns out we'll see that we can easily put some priors on this. All right. So one thing that we can do is, since we're going to be standardizing a lot of data, we should probably just make a function for it. We'll just call standardize. We'll pass in the data, and then we'll just say return data minus np.mean of data divided by np.standard deviation of data. Maybe I should even add this into our, it's probably a good idea to add this into our cheat sheet. So let me just add that in here. Oh, before I forget here, standardizing data. There we go. That's useful. So now we have the standardization function, and now we can just say ice cream s equals standardize data, and then crime, we'll also do it for the crime data. Standardize, and I of course wrote that wrong. And oh dear, standardize. Fix that there. Okay. Standardize of crime, and this is ice cream. And just to show you that really, you'll see that it won't really affect the general results that we take out of our analysis. So let me show you that. So if we were to first try to plot the scatter plot of ice cream versus crime, we should see that, fair enough, it does look like a pretty positive relationship between the two, as promised. All right, and now if we do the same plot, but for the standardized data, what's it going to look like? Well, since it was linear transformation, it looks identical. Right? When you look at the shape of it, it's identical. Because all we've done is shifted this stuff over and rescaled it a little bit. And so now what's really changed is that rather than going from, say, 2 to 9 here, it now goes from around -2 up to around +2 to 3, somewhere in there. It's always between -3 and 3 thereabouts. And then over here, except for large outliers. And then this went from 90 to around 110 to instead being -2 to 2, right? Because all we've done is just rescaled things, but it looks identical. And so what happens is our slope is still going to be just as likely to be, versus positive versus negative. And if we ever want to get it back, we can just rescale the slope, whatever we get for our beta, back into this format if we want. And similarly, for our alpha, we can also rescale it. Obviously it's going to be around 0, but we can rescale it so that way the alpha says, okay, at 100 it should be around 5, or whatever we want to do. So now the only question is, with the standardized data, can we put some priors on? Well, yes, we can, because it turns out that when you do just a basic linear regression on standardized data, then your slope is actually the correlation coefficient. And actually, just part of the definition of just based on how you solve this stuff, it turns out it's the correlation coefficient. And so the correlation coefficient has to be between -1 and 1, just by definition. And so what we can do is that we can actually say that the beta, we know, should be centered on 0, and you can put down whatever prior you want. In the book, lots of times people will put down 1, which is very, very generous, because clearly the normal distribution goes past -1 to 1. When it has standard deviation of 1, only around 67% is between -1 and 1. And so it definitely allows for stuff well outside of that, which are actually physically impossible in this case. But in statistical, we think you tend to use around 0.5, which seems kind of reasonable, right? So we'll stick with that. And meanwhile, for the alpha, that one, the interpretation of this one now is, okay, when the data for ice cream, for example, when the ice cream data is at its mean, what do we expect the value to be for the crime, right? So in this case, it's all in standardized format. And so what the idea is this, is that when ice cream is at its average value, we would expect that crime would also be probably at its average value. And so because of that, its average value is 0, because it's been standardized. So it makes things very easy, because we expect the alpha to be 0 or close to it. And so I believe in the book he ends up using 0.2 thereabouts. All right. So now with this, we should be able to run this, except we can't quite. Not yet. Hold up. First, I have a typo. But importantly, now instead of using ice cream and crime, we got to switch to using the standardized data. Right? Now that our priors are all for the standardized data, we got to make sure we pass that in. Now, of course, I just ran this, and of course, I didn't actually tell it to do anything. So we have to tell it to actually sample too. Right? Posterior equals sample. All right, so now that we kind of beat this whole thing to death, we'll let this run real fast, we'll plot it, and then we'll confirm that yes, indeed, it is that they are quite correlated. All right, summary of posterior. And when we run this, So I wasn't zoomed in very much before, like I typically would be. We see that the beta, first of all, the alpha is sure enough at 0, as it pretty much has to be. But then the beta is 0.5. And the 89% credible interval or compatibility interval is 0.3 to 0.7. So now let's go back to the board and try to interpret this first. And we'll see that A, we need some context, and B, this beta alone, just from the data, it doesn't really tell us anything about causation. Well, it obviously can't because we know this is wrong. All right, but let's talk about it. So, like I said, we have our data here, right? And first of all, what is this data? I didn't even tell you. I told you ice cream sales and crime, right? For all you know, it could be really, really pretty stupid. And this could be each individual data point could be for a certain city in the US, right? And this is total ice cream sales and total crime. And so, really, all that it would be saying, it's saying, okay, cities with low ice cream sales also have lower crime. And cities with high ice cream sales also have high amounts of crime. Now, if this is an absolute numbers, it's kind of obvious that could just be, oh, well, the cities with small ice cream sales, they have less ice cream sales because they have fewer people. And what do you know? They also have less crime there because, well, there's fewer people to commit crimes. If this is number of crimes per day and number of ice cream sales per day, it's like, well, the more populated the city, they're going to have more of it just because they have more of everything with more people. So that would obviously be kind of silly. But the way that you would interpret the beta then is that, like I said, how much more crime do cities with higher ice cream sales have, right? We're comparing different cities in this case. The cities with higher ice cream sales have higher crimes than those cities that have lower ice cream sales. Doesn't say that it's causing it. It's just talking about a relationship that you observe across different cities. Now, what if this is the same city across different time? Well, what it says is that during times that have high ice cream sales, you have higher crime, and during times with lower ice cream sales, you have lower crime. Now that's interesting. Now, if this is once again, we got to be careful here. If this is say over the course of 100 years, you could have the same thing where it's okay. Well, this is a time, and so early on, back in like 1920, you didn't have much in the way of ice cream sales, and you didn't have much crime because there weren't many people in this city. And then as population's gone up, you've seen an increase in both, right? So once again, that's not saying too much. But let's suppose, just for the sake of argument, this is over the course of say 1 year in a city where it hasn't been changing population. Now this is a little bit more meaningful. This says that okay, during times, once again, or during days, let's say, with high ice cream sales, you also have high crime. Now, so the point though is that you're comparing different things, different times, and there could be other things going on between those times that account for these properties. And in this case, the easiest one to explain it is that it turns out that there is a strong connection between temperature and crime. And not a surprise, there's also a strong connection between temperature and ice cream sales. I went to an ice cream store yesterday and night, and it was maybe like 50 degrees out. And I gotta say, I was the only one in there buying anything. But on hot days, ice cream sales are off. I mean, ice cream stores are often pretty busy. Everyone wants to get ice cream, and so I'm not going to get into why it is that there's a connection between crime and temperature. It just turns out there is, and people have tried to come up with good explanations for why it is. It could be genuine causal relationship where it's something like when it's hotter out, then people get more irritable or more rash in their decisions because they're hot. Um, or alternatively, it could be things like when it's hot, a lot of people leave their home to go places because the weather's nice, and then when they're gone, then that leaves more opportunities for burglaries or things like that. Or they're outside more, so therefore there's more opportunities for muggings, things like that. Um, but there's also ones that say, okay, there could be some correlation here where it turns out that it's only hot when it's during the summer. is the most likely time when it's hot. And also during summers when a lot of people have vacation, so they're away. And that means that there's more opportunities. It has nothing to do with the heat. It turns out it's the time of year, right? Which is when people go on vacations. And it's not really because of the temperature itself. And so there's some debate where, okay, there could be some genuine connection there between temperature and crime, or it could be once again kind of like this, where there's some where while there's a connection, where there's some relationship, it's not a real one that's one's causing another. Just like ice cream sales isn't actually causing the crime rate. And so the way that you draw this is you can say temperature causes the ice cream sales. All right, I'll just put an I there. And it also has a causal effect on the crime. And this is just, I'm just going to assume that's the case. And what we're interested in is there actually any causal relationship from ice cream onto the crime? And we know that's not the case. We know it's not the case. But, there's a question for what is, whether or not there is. And in general, what we're seeing here, when there actually isn't, is that there's a confound here. So this is the classic confound, and this is called a fork. All right, and you can see it's forks because there's a fork from temperature in this little arrow diagram here, which is called a directed acyclic graph, or a DAG, DAG, directed acyclic graph. The temperature has an arrow towards the ice cream, and the temperature also has an arrow towards the crime, showing that there's actually a causal effect of temperature on ice cream sales and also on crime. But I haven't specified what that relationship is. It could be linear, it could be highly nonlinear, it could be negative, it could be positive, it could be some sort of wiggle thing like a sine wave, it could be any sort of relationship. It could be something that relies on other stuff to come into play. And so I don't want you to think that this just says there's linear. It's just that we have some broad idea that there's some relationship. And then sometimes we'll just represent these as some linear thing just to keep things simple. It's a statistical model, not something that's very heavily thought about, right? We're just adding a little bit more information in here. Because where is this information coming from? Well, it comes from our own understanding of the world. All right. And so you have this DAG, and the question is, though, so what? Right? Like, how does this, when we run the regression there, we still see that there's a correlation between ice cream sales and crime. And so how do we know that this isn't actually the case that, that in fact ice cream has an effect on crime? How do we know it, right? From the data, we aren't getting this, right? And we can't just say, well, just assume it doesn't. We got to at least have some evidence in the data to tell us. Well, it turns out that if you add and try to adjust for temperature, if you kind of in your regression, you add temperature into the mix, what we'll see is that this apparent correlation will disappear. And so let me first run it with the multiple regression, right? And then we'll come back and talk about how exactly the multiple regression works and how it is that it's actually resulting in us trying to estimate the actual causal influence directly from ice cream onto crime, right? And how it helps us achieve that. So let's take a look at it. So first, let me copy over I actually have someplace else here. I have the data on temperature. I have some temperature data. I didn't copy over before for obvious reasons. Oh, I'm sorry, the lights just went out here. I don't know why that is. This temperature, there's this little sensor in this room for turning on lights, and it is awful. I think it's getting worse by the day. There we go. So let's copy over the temperature data, and let's take a look. So pass in right here. I'll add it in right here. We say temperature. There's some temperature data. Once again, it's I think I actually tried to scale this so that way it looks like standard type of temperatures that you're used to in Fahrenheit, right? So they range from 36 at the low end up to say 100 at the high end. at least look a little bit reasonable, but we'll still standardize those as well. Might as well. All right, temp equals standardize. But you could see why you might not want to, because it could be useful to say for every degree, how much effect does that have on other stuff, right? On the outcome variable. So what we do is first it's useful to kind of name these betas, because we're now going to have two betas in here, one for the ice cream effect, for the effect of ice cream, and one for the effect of temperature. So what we sometimes do is say, okay, this is going to be, this one is, I'm going to call it IC because it's the effect of ice cream on crime. And then we can have a beta TC for temperature on crime. Right? We use the same priors for it. And now all we do is add in a beta TC times crime, not crime, temperature standardized. And we'll change this to beta IC. And now when we run this, we can run this again. And when we get the posterior, you're going to see that the effect of ice cream is just going to disappear. And I'll explain on why that is. Cool. So here we go. So first of all, the effect of temperature on crime is very positive, right? And the effect of ice cream on crime is that minus is now gone from its strong positive correlation down to now being negative 0.18, but our 89% compatibility interval ranges from minus 0.46 all the way up to 0.12. So we actually really are not too sure on what the effect is. It could be negative, but there's also a decent chance that it's a positive effect, right? Or we can just say, well, there's not strong evidence that there even is. Well, we can't say that there's no evidence that there's a strong effect because, if in reality it was a minus 0.4, it'd be pretty strong correlation between the two. But we don't have enough, so we still have pretty wide error bars. But, the error bars definitely include 0. And so to show that, we can do the rvis.plot posterior. We can pass in the posterior, and it'll make nice little plots for us here. That'll highlight the mean and the HDI. So here it is for the alpha. This is where we think alpha is. It's pretty much right there on 0, and it can range from certain values. There is beta IC. Once again, here's 0. So it could be negative, but also be a little bit positive. In reality, once you see the way I generate the data, it's 0. It's actually exactly 0. And then finally, right here, we have TC, and then you can see that there's some relationship between them that's definitely positive between temperature and crime. All right, and this is the sigma, and who cares about that, right? So now, and of course, I didn't plot it, but if you're interested in doing so, you can do the plot.scatter of temperature with crime, and we'll see that, yeah, it looks pretty positive. But then also temperature on ice cream, and you'll see that that is also quite positive, as I kind of speculated on the board. So what's happening here? What is this multiple regression doing to somehow eliminate it, so that way when we look at the regression coefficient, it's actually measuring this connection here and coming up with 0. Why is it getting rid of the connection? Well, the way it works is conceptually, when you do a multiple regression, well, in reality, it's passing some plane through the whole space in this three-dimensional space. But one way to view it is that you take, for example, temperature, and you have ice cream here. And I said they're positively correlated, right? Right, we looked at that data. And so what you do is you fit a regression through that, all right? And the idea of it is this, is that you want to be able to know what the effect of ice cream on the crime is. But the problem is that whenever you change the temperature, they're both changing. So what you would like to be able to do, ideally, is say, okay, suppose we fix temperature to be 30, like say 70 degrees out, right? And now we looked at all the different ice cream sales when it was 70 degrees out. Was there any connection between that and the and crime? Because if so, then we know it wasn't temperature that's causing the difference, right? If what happens is that when we take a little slice here at 70, for example, and we see, okay, well, sometimes at 70, ice cream sales are a little bit low. Sometimes they're a little bit high, right? Maybe I'll draw these with a little different color here just to emphasize that they are high, higher than what you'd expect based on the temperature, right? Now what we do is we look at those same days on ice cream sales versus um, versus crime, and we'll see that, and we'll say like ice cream sales residual, where this is now when you have when you say, okay, how is it relative to what you'd expect based on the temperature? So these right here, they have lower ice cream, right? Let's say like that. And these have higher ice cream sales. If what we saw was this, right? Or let's actually make it even more so, right? So when it was 70 degrees and it turned out we had higher ice cream sales than expected, or in the days where it was 70 degrees and we had lower temperatures, lower ice cream sales than expected, we saw lower crime, right? If we saw this, then we say, well, maybe there really is something between these two. Why? Because even after saying that it's just 70 degrees, on days with lower than expected ice cream sales, we got lower crime, and those with where we had higher ice cream sales, we got more crime. But if on the other hand, whenever we look at those that tended to be higher versus lower, and we see that there's no real connection, right? If we saw that there wasn't any real connection between them, then we say, oh, well, then we have a good idea that, well, okay, anytime that we account for the temperature, there is no real connection left between crime the and the ice cream, right? The connection goes away. And so that's what the multiple regression is actually doing, is that it first kind of takes this regression of temperature on ice cream, sees the connection, and says, okay, now with residual, what's the connection? It's not seeing anything. Meanwhile, if we did the opposite, which it also does at the same time, where it says, okay, take the ice cream sales and figure out, and use those to try to predict the temperature linearly. And on days where, we have, say, a lot of ice cream sales, sometimes, the temperature is a little bit higher than we expect, and sometimes a little bit lower than we expect. When it's lower, do we see lower crime? When it's higher, do we see higher crime? And in fact, yes, you do. And so that gives you the idea that, whoa, well, maybe there really is something between this temperature and crime business. And so when you add to the regression, it's going to capture that, and then the beta is still going to be positive. All right. And so that's the basic idea of what you're doing when you're adding in the multiple regression. Now, what people call this, there's a lot of different names for it. There's like controlling. So it would be, okay, run a regression of ice cream sales on crime, controlling for temperature. We don't really controlling for it. That's kind of a bit of a strong term just when you look at it. And, while statistically, if you know the definition of it statistically, it sounds fine. If you're kind of new to this, the word control sounds pretty strong, right? It's not we're actually like controlling it like a bad boyfriend or something. We're so there's other names like adjusting, which is a little bit more a little bit kinder. And so you say that what we're doing is linearly adjusting. Now, one of the problems with this is that still, if the data was highly nonlinear, right? Maybe I can't really draw nonlinear very well, right? But then we try to fit some line to it. You might still have some problems because, well, things that are below, there's not a clear pattern always. And so when you try to linearly adjust, you could actually end up in trouble because you don't actually get a good fit either way, right? Sorry, let me do it like that, right? And so it is key to understand that when you're doing it, you still want to try to fit the data pretty well, because if you're totally missing the boat on it, you could get some bad adjustments and stuff. And so lots of people will specify right now you're linearly adjusting for temperature when you add it in there. All right. And what we see is that when we do that, what we say is that it blocks this effect, this correlation that's coming in through the temperature. All right. And then once we've blocked it, now we're seeing the direct causal effect of ice cream on crime, assuming that there's no other thing, right? It's always possible that there's some other data that I haven't shown you. Maybe we'll label it U, which could be like the population, right? And the population density, for example, influences ice cream and also crime also for some reason, right? When more people are together and they want to socially hang out by going to the ice cream store, or alternatively, they want to socially hang out by robbing a bank, you know? And so that's what happens when you live close together, you know. I've been tempted a few times. And so with this, you might still see, you know, if you run this regression with the three of them, just these three, you might see still some correlation. And even there, you can't always say for sure that, okay, well, therefore, you know, it's this, because it could still be some extra effect that you have accounted for. And so one of the things that's kind of tricky with this is that you really have to think through what are the connections between all the variables you can imagine, right? If you want to actually measure what the direct effect is between ice cream and crime, you got to sit there and say, okay, well, temperature could affect both, maybe population density, maybe all sorts of. You got to actually really sit down and think through it all, like you would if you were trying to come up with an actual model. And then what you have to do is you have to try running a regression, collecting the data you can, right? And try to see if you can actually isolate the effect between the two. All right. Because if you do that, then you can actually say something like, okay, if we were to increase ice cream sales, let's say we went into Baskin Robbins and Baskin Robbins holds a big sale where they're giving away ice cream for free, we can expect an increase in crime that day, right? Or if we go in and we shut down all the ice cream stores, we could expect a large decrease in crime. And so what's really cool about it is that once you actually get the true causal effect, or at least try to isolate it and think you've isolated it, you can actually talk about policy, right? You can do what's called counterfactuals, where you say, okay, suppose I go in and actually change one of these values while holding everything else constant, or at least, you know, holding, you know, I go in on a 70-degree day and I actually close down the ice cream stores. How is that going to affect crime? It might be something that you never actually observe, right? Because on a nice, you know, sunny day, we always see lots of ice cream sales, right? So now we're going outside the observed data where we actually say, well, on a nice sunny day, we're going to close down all the ice cream stores and we're going to have zero sales. We've never seen this data before. We're going well outside what we've observed. And now we're trying to say, well, what's actually going to happen to crime? If you try to use simple prediction analysis, you know, neural network, it's not going to know because you're now outside the range of data it's ever seen. But for us, we now have some theory talking about the causal effect of one another, and we can actually talk about what's going to happen. Now, in reality, we know if we close down the ice cream stores, probably not actually going to affect crime, right? Now, one thing I want to also point out, though, is if you're just in the game of trying to do predictions, you don't care about this stuff, right? You know, I mean, well, technically, temperature probably does a better job of predicting crime than ice cream. But if you didn't have temperature and you're just trying to predict uh, the crime rate, it's not a bad idea to use ice cream, right? You use the ice cream sales, and hey, it's correlated, you know. So sure, you know, if that's the only X I have, I can use it to start trying to predict some of my crime rate. Now it's not causally related, but you know, it helps you for doing predictions. So if all you care about is actually predicting the crime rate, you're welcome to include the ice cream in there if you don't have and use it as kind of a proxy for the temperature, right? When you're doing causal analysis, it just doesn't cut it. If you just do ice cream on crime, you get the strong positive result, and it's not actually real, and you shouldn't be interpreting that way. So now let's just do a couple more examples. They're going to be kind of quick, all right, because I know I've already been spending a little bit of time on this, going a little bit slow. The next one I think is kind of an interesting one, where before I do that, let's just do one quick thing here before I forget. I wanted to show you the actual data generating process. So I told you that I generated this data manually. And what I did was I rescaled them after I did this a little bit, just to get them into like different ranges of values to show you the whole idea of scaling. But I'll post it right in here. Here's the actual thing I used to generate the data. I just took temperatures to be some normal distribution, about 50, scale of 3. Like I said, later on, I think I scaled it up some so that way it's in normal temperature ranges. And then ice cream had a mean that was equal to whatever the temperature was. And it was just some variance around that same temperature. That was all it was. And then meanwhile, crime was centered on 5, and then I added 0.3 times the temperature, and it had some variance in there. So what you can see is that the actual crime rate clearly went up with the higher the temperature, and so did ice cream. Right, and with this, we ended up with these type of results. But obviously, right here, the ice cream had no effect on what the actual crime rate was when we generated the data. So so the effect that we saw originally was truly just wrong. All right, it wasn't a real effect. So now let's go into this new data. All right, and this one's kind of cool. Like I said, I think this one's kind of interesting. We have 3 different variables. All right, we have the price of some good. Right, the quantity that was produced. All right, so this is the quantity produced of some item. Here's the price, and finally, you have the number of unsold goods. And what we're interested in is how do price and quantity affect the number of unsold goods? All right, so let's take a look at it. All right, hey, look, this is an economics course. We got to throw in some economics here, right? So let's take a look at it. So here we go. Here are the prices. Here are the corresponding quantities, and here are the number unsold. And you can assume that these are across days or something like that. We'll give you some context. All right. So we get the data there. Cool. Let's fit a model to it. Let's first take a look at some of the plots. Scatter. Let's do price versus unsold. Right. We probably expect that as you up the price, you're going to sell less, so you have more unsold. And so we expect this to be positive, perhaps. And it looks not particularly positive, does it? All right, let's also look at the plot for the scatter for the other one, which is the production non-sold. Well, clearly, if you just produce more of something and you're not selling anymore, you should have more unsold. Oops. Production versus unsold. No. What have I done here? Oh, quantity. Quantity is what I call it. I think I originally called it production, but then I didn't like the name because then they both price and quantity, price and production start with P. Once again, no real connection there. Once again, this is by design. In the book, he actually has some real data that fits this exact pattern, where you might expect some connection, you're seeing 0. And so I'll tell you right now, I'm not going to do it. If you actually fit these regressions, you will see that it sure enough is 0. Let me see. Maybe I can actually copy over the code because I don't want to spend too much time doing it, but I think I might have it here. Yeah. All right. So let's do that. So let's actually, I'll quickly, since I can just copy them over largely, I'll do it. So we'll say price test. Let's just standardize these because once again, I don't know what the ranges are or anything like that. I'm not going to pretend to know. So we'll standardize price. We will quantity S equals standardize quantity. And finally, unsold of S will equal standardize unsold. All right, so we'll normalize all that stuff, standardize all that, and then let's run a quick model trying to predict based on the price. Let's predict the unsold, right? So I gotta change this around because I think I used a different variable name when I actually tried running these in the past. Unsold. That should definitely read unsold. guy also had some typos in there. Doesn't really matter. And there we go. Right. Beta. Right. So price on unsold. Right. I think I got it all. Let's run this. Let's take a look at it. And we'll say az.summary posterior. And whoa, what have I done? 1 second here. I've clearly made some sort of error there. Oh, I have the muse in there. I think I was just testing some stuff out there. You don't need that. That one's in the cheat sheet. It explains what you're doing there. It's more for when you're trying to do some of the predictive stuff. Not important here. I'm gonna get rid of that. But as you see, the beta, it's centered on 0.133, which is positive, which says that the higher the price leads to more stuff unsold, which makes some sense. But there's quite a bit of uncertainty in there, right? And so it's not a surprise if we want to, we could plot over. You can maybe see a little bit of a, I think part of it is this one data point is probably driving it to look pretty positive. But if you dropped, say, if you ignore this one point, if I scrolled up just a smidge, let's say it didn't show up, you'd be very hard pressed to say that that's a positive relationship. So I think that's partially just driven by the outlier there. And even still, you aren't that sure about it, right? If we plotted it, you'd see that there's a lot of the probability is weighted in the negative there. So it's nothing so it's not particularly, we can't really say anything with any sort of confidence. Meanwhile, if we toss in price, if we do it for, instead of price, we do it for the quantity. Actually, here, let me just say price here, and then I will S price quantity. There we go. So now I've switched this to be quantity. Oh, and I got to change these to be QUs to be consistent. And now we should be good to go. And now we'll also run, take a look at this guy, summary. So if we try to run each one of these individually, sure enough, this one looks to be slightly positive, but once again, also a lot of uncertainty there. I wouldn't have even guessed that it would come out positive with this one. Yeah, I don't even really see anything positive there. But, whatever. Who am I to say? All right. So now finally, let's throw them both in together and see what happens. All right. This is what we've been waiting for, of course. I'll call this like the PQ. And so now we just need to have the beta PU in there. All right. And then we just have to add in a beta PU times price S plus that. So now what's going to happen? Let's take a look at it. This is where things get a little bit exciting. az.summary of posterior. Oh, what's going on there? Acceptance probability. Yeah, we can increase the tuning, but it's not a serious issue. Okay. So here, now look. Now they're both strongly positive. Look at that. Between 0.4 and 1.2, between 0.4 and 1.2. So that's pretty darn strong, isn't it? What is going on here, right? When we look at each one individually, they don't look like really anything. Right? I wouldn't hang my hat on any of this. And yet, when you toss them both in, you're getting a very strong correlation between, or a very strong relationship between the two, between each one of them with the unsold. What's going on? Well, this is a masked relationship. And one way that you can see this is if we do the scatter plot of price and quantity, it turns out they are tightly correlated with one another. So what's going on here? Let's look at it on the board. What's happening is that it turns out whenever price is high, let's say 80, 100, then quantity goes down, right? So let's say, and this is quantity of production, right? This is how much we produced. So maybe I should have called it production, right? The quantity that we produce or supply goes down. And so now it turns out that even though the price is higher, whenever the price is higher, we produce less. And so even though we might sell less because we have lower prices, we also produce less. And so the number unsold remains largely the same in both of these. Let's say it's like 10 in each case, right? When we lowered the price, we also increased the how much we were producing. And so at the end of the day, about the same for unsold. And so what's going on here is that we were interested in the number unsold. We were saying, oh, well, maybe price is affecting that, right? The higher our price, the more it's going to be, left unsold. And meanwhile, at the same time, we said, oh, but also the amount that we produced should also lead to more being unsold, right? And once we actually put them all into one regression, we did find that. But when we looked at it individually, they weren't. And so there's a few different possibilities. One is that the higher price is somehow leading to a lower quantity, right? So whenever we raise our price, somehow that leads us to produce less. That's one possibility. A second one is almost the same. It could be that whenever your quantity goes up, that's causing you to reduce your price. Whenever you produce more, you're lowering your price. Or the third possibility is that this is actually that they have some confound, some common confound, where you have price, quantity, and then you have some other thing here, which I'll label like X here, just because I don't know what it is. And I don't want to use U because I'm using that for unsold, which is somehow affecting both. So when something is going on here, let's say like the manager in charge, he tells them to say raise their price, but also lower their quantity, or vice versa, right? This could be who's in charge. We don't know. There could be some extra data out there that's causing this relationship between these two, and it's masking the effect of it being on of the amount being left unsold. And so what's happening is that, for example, to figure out the effect, and we'll talk a little bit more about this in a little bit about how it is that when you include them all in a regression, it turns out that it takes care of this. Right? It actually helps resolve this and isolate the individual effects on each one of these. Now, in reality, which one actually does this? Because remember, I generated this data. The actual one was this one is the true one. You can't currently distinguish between them. This data alone and the results that we got are consistent with any one of these. But I think this one was the actual true one, because what I had done was that I had pretended that it was kind of like a farmer when I generated the data. So the farmer, he grows some stuff. Maybe he has a good year, and so he's going to produce a whole bunch. He goes, well, I want to try to sell everything out, so sell all my stuff that I made a whole bunch of extra corn this year. I'm going to lower my price. That way, I pretty much try to sell everything and maximize my profit. And meanwhile, if it's like a bad harvest, oh, I don't have very much, so I'm going to charge more, and then that way, I'll just sell what I have, at a higher price, maximize my profit. And then so I got like a really simple demand curve in there, and it generated this data. Now, I didn't tell you that context. And if I did tell you it, you might have actually been able to build this type of model and actually write up a demand function and get some more useful mechanistic model out of this. But that's something that we'll hold off and we'll do, like I said, next week we'll do a mechanistic model, and it's pretty cool. But going back to our data here, let me show you this. Here's how I generated the data. Once again, I think it's pretty useful. Do this. There it is. So you can see that production was just some random value, right? This is our harvest for the year. Oh, I should change this to quantity. Right. Sorry, I did that. All right. So that was the idea of, like I said, just a harvest from a farming crop was my thinking. And then the price, you decrease it the more that you produce, right? You say, okay, I'm going to reduce my price. And then finally, right here, you have the amount unsold, or I called it spoilage at one point, that I thought made sense, but I'll call it unsold here, just to be consistent. It is the quantity that we actually produced, right, minus how much we sold. And for that, I just plugged in a simple demand curve where you sell 35 minus some amount based on your price. And so at the end of it, we get our number on sold. So that's how the data was generated, in case you're curious. So now let's move on to one more, where so far all that you've seen is, okay, well, if I just throw in all my variables, I control for everything, I adjust for everything, and I'll isolate the direct effects, right? You wish. That's not the case. That's definitely not the case. And if you just toss every variable in, you are in for a world of hurt. All right? So here I'm going to give you one more example where, in fact, the opposite is true. Where when you throw in the variable, you get the wrong answer. All right, so I'm going to actually tell you how I generated this data right off the bat, and then we'll actually go through and look at what happens when we try to fit it. So what this one is that let's say you're taking a class, and there's a lot of different students in there, and they put in different levels of effort. All right, and I'm going to assume that this is just normally distributed. Similarly, some of them have some different various innate interests or talent in the class, so we'll call it aptitude. And what we're interested in, is there any relationship between how much effort somebody puts in and what their base aptitude was? That's what we're interested in. All right. Or maybe I'll switch to the X and Y just to make it a little bit more interesting, right? Because this might be a little bit more of our causal idea here, which is that we might have this question of aptitude. Does that affect your effort, right? That's our question, right? So if somebody has some just really good talent, does that mean that they're lazy and they won't put in as much effort in the course? And or vice versa, where somebody who maybe doesn't have much aptitude, natural talent for this topic, they put in more effort to make up for it, right? So I'm going to tell you right now, in the data that I generate, there is zero relationship, right? It is just a straight up normal distribution between the two, all right? And that's it. Zero correlation, all right? But what we're going to do is we're then going to look at how we can accidentally find a relationship between the two when there actually isn't. All right. So let me actually go here, and I'm going to show you the data. I'm going to show you the data ahead of time. All right, on how I generated it. So let's see here. Here it is. So I have aptitude right here, which is just a normal value, normal distributed value, centered on 5, standard deviation of 2, where I grab 100 of them. Effort is also just a normal, normally distributed value between mean of 5, standard deviation of 2. Let's quickly plot these. Plot.scatter, aptitude, and effort. So if you tried to do it, you would see it is a big wasteland of nothing, right? And sure enough, if you fit this, you're going to find that is nothing, right? We'll quickly do it just for effect here. I'm going to definitely copy this over because you've already seen me fit a couple. I think you get the idea on how to fit regressions here. Let's see here. Let me just pull this up. It's going to take me just 1 second here to find it in my other file. Here we go. So we can standardize these things first. So let's do that. So we standardize the grade, the effort, the aptitude effort, and grade, which I'll explain the grade in just a moment after I fit the first model here. All right. And where this comes into play. So here's aptitude on effort. And now let's just do the az.summary. And this is obviously, we know it's 0 just by looking at it, and we know what happened here. Here we go. Minus 0.112, and it straddles 0, right? I mean, I know that, when we looked at it, it looked like it was pretty clearly nothing, but it still picks up something that's almost negative here. Just for effect, I'll run it one more time with the new set of data, and we'll see. Probably be a little bit closer to 0. If I had enough data, we don't only have 100 data points. It can easily mistake it into thinking that there is an effect. Here, it's pretty darn sure, or at least that there could, it could be slightly, it's a normal distribution on what it comes up with. So it could be, it could happen to be a little bit far on one side. But just to really show it to you and drill it home, I ran again with some data where it's very clearly pretty much 0, right? Now let's run this again, where now we add in what grade they got in the class. And what their grade was, very simple equation. It's just the average of their aptitude and their effort. That's all I did. I took the aptitude plus the effort divided by 2. So the average student gets a grade of 5 in the class, right? And then somebody who says average but a little in aptitude but a little bit higher effort gets a little bit higher grade. And someone who's low on both gets a lower grade, right? Nothing big, right? Now let's make that one, right? So this one's easy enough to do. All we got to do is toss in. We have the alpha and beta, and it looks like I used slightly wider priors. I could switch this to be consistent with the book of 0.2, 0.5. It doesn't matter, right? We have enough data to overwhelm them. And now we have, okay, here's our multiple regression where we have our effect of aptitude on effort, and then also the grade on effort, right? Easy enough. Want to control for their grades, even though there's no real causal explanation for why their grades would somehow affect their effort. Well, maybe you could say, okay, well, maybe if they're doing well, they're going to put in more effort to make sure they keep their grade up or something like that. You can come up with some explanation, I'm sure, to include it. So let's take a look at it now, right? Is it still 0? Ooh, this guy is now strongly negative correlation between them. Effect. Wow. If you made the mistake of just tossing everything in and thinking that was correlate or causation, you would be saying that, okay, the more aptitude you have, the less effort you put in. And you could put up a little, make that be the title, maybe come up with some snazzy title about how you get lazy the smarter you are or something like that. And you could publish that. It's a strong result. Strong result of nothing, right? But it certainly looks strong. So what's going on here? What is going on here? Well, what we've made the mistake of is adjusting for something we shouldn't have. All right. And I'll show you on here what's going on too in the graph. All right. What's actually happening, as we already know, because we looked at how we generated the data, we know for sure that this actually is not there, but that your aptitude and your effort both affect your grade. All right, that's the shape of what the diagram looks like. And it turns out that in this case, if we want to try to figure out this and we include grade, we get in trouble. This is what's called a collider bias. All right, and to understand it, it's a basic idea. Right, just like how we were saying, okay, suppose that the temperature is fixed at 70. How does people, how does it affect, right? Well, let's look at it. Let's suppose we took a slice of people who say got the equivalent of a B, right? They would be kind of in this range here, right? Because if you got a B, right? If you had really high aptitude and really high effort, you got an A, right? If you're low on both, you got a C or lower, right? C or lower. Um, but for a B, you either had to have relatively high, say, effort and kind of maybe a little bit lower than average aptitude, or maybe a little bit higher than average aptitude and maybe a little bit lower than average effort, right? Or maybe a little bit above average or both, right? But if we sat here and we said, oh, well, you had a high aptitude, well, okay, the only people with high aptitudes that got a B must be because they didn't put in all that much effort, and vice versa, right? The people who put in a lot of effort and only got a B, well, they must not have had that much aptitude going into it. That's what we actually know just by thinking about it. And so the problem is that once you introduce the grade and you start saying, okay, adjust for grade, consider the people who just got Bs. Is there a relationship there? You betcha there is. Among people who got Bs, those with higher aptitude put in less effort. Why? Because if they had put in the same amount of effort, they would have got an A. And we're saying we're considered the people who got Bs. So it turns out by adjusting for grades, we've screwed everything up, right? We're now suddenly seeing that there's some negative correlation going through each one of these, right? it wasn't actually there when you compare the two or in reality. But once you adjust for the grades, all bets are off, right? And you think of it, just like what I did with the temperatures, where you look at the residual and you say, okay, well, among the people who got a 70% in the class, those who had lower than expected aptitude, oh, well, they must have, to have gotten a B, they had higher effort. And so you see a correlation there, a negative correlation between the two. It's an interesting problem. And so we'll talk a little bit now about exactly how do you figure out which variables do you include? Because, like I said, sometimes they fix problems and sometimes they screw them up when you add them in and adjust for them. So, how do you figure it out? Well, when you look at these directed acyclic graphs, it turns out that there are only 4 real patterns in them that you see, components to making them up. And some of these things, all the ones I've drawn so far have been kind of small, maybe like 3 or 4 letters at most. When you really get into it, there's ones with like 20, 30 letters. I've seen some that are really incredible just for like doing medical analysis and stuff. There's just a bajillion of them. Everything's affecting everything with the body, right? But there's, in general, only 4 components, right? And we'll talk about each one. The first is the fork, which I introduced first. And that one looks like A, B, C. Right? And it's a fork because you can see from A, there's 2 things that fork, right? And what happens with this one is that you will see a correlation between B and C. If you just do a basic regression on it, all right? But, and so what we call this is that the path, there's a backdoor path is what it's called, where even though there is no direct effect that B has on C, you will measure a correlation because it turns out that when you do the regression, that slope can pick up the effect through A, pick up the effect, this fork from A. And so in this case, you close the backdoor path, you close it by adjusting or conditioning in general is what it's called, by conditioning on A. So we say given a certain level of A, if the temperature is fixed at 70, can we see any relationship between B and C? So when we condition on A, we close this backdoor path, and now we'll pick up just the direct effect between the two. And in this case, it won't be, it'll be 0 in this case. So that's number 1. Number 2 is the pipe. This one looks like A affects B, and B has an effect on C. And this one is largely the same story, right? Well, this one's kind of interesting, right? Because B actually does have an effect on C, right? And A also has an effect on C, but through B, right? So this is like, okay, the temperature goes up, that leads to more ice cream sales, and it turns out the ice cream sales is what's causing the higher crime rate. Oh, no. Or you can think of it, or the way that I was describing it before, higher temperatures lead to more people leaving their houses, that leads to more robberies because there's more opportunities, right? And so in this one, you'll definitely see a correlation between A and C. In general, you will. Of course, now it's a little bit tricky. If this one's positive, this one's negative, it might end up being a little bit masked. So you gotta be a little bit careful on that. But there is a way for the information from A to then be seen in C. And once again, if you condition on B to close the path. So in this case, if we say add A, B, and C, say temperature of people leaving their house and causing more crime, and then we said, okay, well, conditional on the number of people out of their house being the same, is there any effect of temperature on crime? We wouldn't find anything, right? Because the only way that temperature actually affects crime in this model is by increasing the number of people leaving their houses. So if we adjusted for the number of people leaving their houses and said, okay, conditional on it being the same, half the people are gone, on a hot day versus cold day, does that affect crime? In this model, no, it doesn't, if this was the true. All right. And so then the third one that we're going to talk about is the collider. And by the way, just real fast, I believe that the one that we had was something like price, quantity, and then unsold. And what we wanted to know, for example, is P on U. And so when we're looking at P on U, the problem was that we were picking up a fork, right? Quantity was affecting both the price by decreasing it and also increasing the number unsold. And so the problem was that when you tried to just measure directly the effective price on the unsold, you're picking up both these effects, unfortunately. And so once you included quantity, then you were able to close this path, and now you were able to get the direct effective price on the number unsold. Meanwhile, if we wanted to know, now here's an interesting question here. Suppose I want to know the effect of changing the quantity on the amount unsold. Well, it turns out it depends on what you're asking, right? Because here you can interpret it two ways. One is that I could be asking, okay, suppose that I held everything else constant, like the price, and I just increased the amount I produced, right? Would that reduce or increase the amount of quantity that I had unsold? Yeah, it would increase it, right? Intuitively, that makes it, and according to my model, it would increase it. But the problem is that in reality, any time that my quantity goes up, that leads me to drop my price, and my number unsold ends up remaining around unchanged. And so it depends on what you want to measure. Do you want to measure the direct effect of changing just the production, the quantity on the number unsold, or do you want to know the total effect? Where when you happen to have a good harvest, yeah, that's going to, because you are putting more in the market, that's going to leave more unsold naturally. But because whenever you have a good harvest, you lower your prices, and so you end up with the same amount unsold. So the total effect ends up being zero. And so there's a debate always on if you're interested in are you interested in the total effect or are you interested in the direct effect? And sometimes we can ask which one are we specifically interested in, and then based on what our answer is, we run different regressions. If we're interested in the total effect, then we want to have all of this. And so in that case, we want to leave this pipe open. We don't want it to close because we want to see the effect that the harvest has on the total amount sold through its change in price. That's part of the effect, and that's part of the thing that we want to measure, right? And the second part we want to measure is the direct effect. So in this case, we don't want to condition on price because we want to leave that open. And so what we would do is that if we wanted the total effect, we would just regress. We would just do a regression with Q, and we wouldn't include P. If we're interested in the direct effect, then we would want to include P and close off this effect to see the direct effect on the amount unsold. All right. And so it actually depends on what we want to measure. All right. So anyway, now the third one's the collider. And this is the one with the aptitude and effort. And that one looks like B affects A and C also affects A. And for this one, it's closed by default. If you run B on C, you find no correlation. Right? No relationship between the two. If you just do a basic regression on B on C. When you condition on it, conditioning on A opens the path. And so what that means is that once you toss an A, you will now see a relationship between B and C, just like we saw there, where suddenly once you include the grade, because clearly your aptitude affected your grade, and so did your effort affected your grade. But when you conditioned on grade, you suddenly saw an effect between these two that was not real. All right, and that's what a collider does. And it turns out that a lot of places in out there, people accidentally toss in a collider, and suddenly, boom, their entire regression gives erroneous results, and they try to interpret them causally, and they're in deep trouble. All right, because suddenly it'll say, oh yeah, well if they put in more, if they put in more effort, then they have more aptitude. Or oh yeah, if it turns out that this person, right now they put in some certain amount of effort. Well, if we put them in a class that they really like, we know they're going to put in less effort. And like, no, that's not necessarily the case. That was just a collider bias that you accidentally conditioned on. All right. And the last one is the descendant. And this one isn't that interesting to me. I mean, descendant. So I don't know if there's an A. One second. I gotta check the spelling here. It's an A. I knew it was an A. I knew it. I just wrote it down. Descendant. I'm actually a very good speller. It's just when I'm on the board, I'm not. All right, so here's descendant. And what this one is, in general, it could be any one of these, right? But the catch is that there's going to be like B, C, A, and then you have a D here. Right now, in this case, I drew it as a collider, but it could also be, for example, let's take a pipe here, like A to B to C, and then there's a D here. All right. It's a descendant where it kind of is one of these, but then there's also something that it causes also. The one in the middle causes a descendant. And in this case, what happens is that if you conditioning on D partially conditions on the on B, or well, on the parent. All right. And so this would be like something like, okay, instead of say doing it on the grade, you do it on say, you know, whether or not they were on the dean's list, right? Or something like that, where okay, maybe they're rather than right here where here's grade, right? Having high grades in all your classes leads to you being on the dean's list. And so if you condition on the dean's list, it depends on how strong the relationship between these two are, but it's effectively like at least partially conditioning on the grade. Depends once again, it could be like, okay, based on how good of a job they got coming out of college. Well, if you got higher grades, you're probably going to get a better paying job. And so once you condition on that, then you might also still see somewhat of a relationship between the two. But once again, it kind of it depends, right? It depends on how strong the relationship is between the two. All right. So those are the four. And the idea is that if you want to get the direct causal effect of one variable on another, first thing you gotta do is actually come up with your directed acyclic graph for the relationship between all the variables. That's the first task. If you can do that, then what your goal is to then figure out how to measure the effect between the two without picking up a whole bunch of other confounds or accidentally conditioning on a collider. Figure out what variables you have to include in your regression. All right. And then if you can do that, sometimes it's not possible with all these graphs, but oftentimes it is, then you can at least have a little bit of confidence that maybe you can actually say something about the effect of one on the other causally. All right. So let's just do a couple quick examples and I'll be almost done. I think I probably have another 10 to 15 minutes worth at most. All right. So let's just do two quick examples. I'm going to take them straight from the book. All right, let's hear. Wow, already have an hour and a half. I'll be done in 15 minutes. All right. So the first one they got here is X, Y, U. He often uses U to signify unknown or unmeasured stuff. some other variable that we don't quite have data on, but we know it affects things. All right, so here's the DAG for this slightly complicated version here. All right. So the first thing that we want to know is we want to suppose we have all this data. We don't have U, but we have data on X, B, A, C, and Y. And we want to measure the effect of X on Y. All right. So what we got to do if we want to do it is first, we have to figure out all the different paths, the paths that aren't actually, X actually causing an effect on Y, right? We have to figure out all the alternative paths. And specifically, what we're interested in is these are called backdoor paths because, for example, right here, there's this path from, say, X that U has on X, right? And then U also has on B, and then C has on B, and then C has on Y. So this is one path that we could draw from X over to Y. And in it, you can clearly see that it's not X causing this whole chain of events. It's other stuff affecting X. All right. A second path is to go up and over, right? Which would be X, U, and then A, C, Y. All right. These are the two paths. I don't think there's any others. You can try to look for one, you won't find them. All right. Paths from X to Y, this is not the direct path, right? These are the backdoor paths. All right. So step one is to list the backdoor paths. Step two is to figure out, okay, which ones are currently open? Which paths are open? Okay. So what do I mean by open? What that means is that what you do is you look at each individual part and figure out whether or not they're open. So let's look at it. So this U between affects both X and B, right? And so that is a fork. And we know from just that example with ice cream and crime that and temperatures that this one you're going to pick up a correlation between the two. These are open. This is an open path. All right. So far. But now when we look at the B here, this part right here, this is the collider. So by default, if you don't include the B in your regression, this part right here is closed. All right. So because of this part right here, this is closed so far. And then finally right here with the C between B and Y, that's another fork. So that part would be open. So this part's open and this part's open, but this part is closed. All right. And if any part of this pathway is closed, the whole path is closed. So right now, if you just looked at this right here, you would not, if you tried to do X on Y without conditioning on any of these three, this pathway, you wouldn't pick up any spurious correlation. There'd be no extra little confounding correlation there. What you would be picking up would just be X on Y. If all we were concerned about with these two paths here, it would be fine to just do X on Y, and you would be perfectly fine. But there's this other path we got to worry about. So let's look at this one. So here you have a pipe from A to U to X, and we know pipes are open. So currently, that part is open. A affects both U and C, and that's a fork, and forks are by default open. And then finally, A and CY is also a fork, right? And it's not a fork, a pipe. And so pipes are open, so therefore you can pick it up. So it turns out when you do this, you can already imagine it. Every now and then A changes. Let's say A goes up or down. And what that does, when A goes up, let's say that makes C goes up and that makes Y go up. Simultaneously, when A goes up, say U goes down, and that makes X go down. So now suddenly what happens is when A is changing, X goes up and X goes down and Y goes up. So now you're going to pick up some correlation between the two, right? But it's not because of X affecting Y. Whenever X goes down, Y goes up. It's because A is changing, and that's through C and through U is changing X and Y. So unfortunately, this one is open. So if we were to run this regression right now, you would get some confound based on A changing and having effects on each one of them. So what we got to do is close it. All right. Now, luckily, since this is let's see here, this is a pipe, this one is a fork, and this one is a pipe, we know that we can just easily condition on any one of them and that'll close it. Now, we can't condition on U because we didn't actually observe U. So we can't toss that in our regression. But we can regress, we can add either A or C in. Either one will close this path. If we add either one into our regression, it'll close it. And then once we've added either A or C, that one's closed. And we got to just double check real fast. That doesn't, well, if we condition on A or C, is this one still closed? Yes, because the only worry was that if we added B in, it would open it up, right? If we added C in here, now what we see is that this part's closed still, but now also this one's closed, right? This fork part was also closed. So it's like doubly closed when we add on C. All right. And so that's cool. In general, if you had to choose between which one to toss into your regression, probably C might be a little bit better just because it has, because it's going to be able to better help affect the variance on Y. And so you're going to control for the variance on Y a little bit better. So you might get a little bit stronger estimates, but it doesn't really matter which one you do. All right. You also have to take into account that you have to always kind of worry that maybe there's more letters. You know, there's always more letters around. And you really got to think through it because what happens if, oh, you know, there's this other letter in here, like say, going like this, another unknown, U2, that goes like this, right? Well, now there's this third pathway here that doesn't include C. So you include C, and now suddenly, you know, this pathway is still open. So you got to be careful. You really want to think through things and decide, have I really captured all the different pathways? Have I really captured everything that's really significant that I need to worry about? Because if not, there could be another confound just hiding around the corner causing you trouble and getting spurious correlation. All right. That's example one. Let me do a second example here. This one is actually from the book, uh, actually from some data they're looking at, which has to do with divorce rates in the South and with Waffle Houses. So you have W, S. So they want to know if the restaurant Waffle House causes divorce. So that was our question. And then I'm trying to remember the arrows here. I'm just doing it kind of from memory here. Marriage and age, I'm not quite sure actually which order it goes in. Let me see here. Marriage and age. Do it like this. Marriage, age. And then there we go. It's quite a lot of arrows again. So what we're interested in is what's the effect of W on D. All right. So let's look at it. We got to list the backdoor paths, figure out which ones close or open, close all simultaneously. So let's start off here. So what are the backdoor paths here? There's actually a lot of them. You might want to pause and try to do it and draw them yourself. And once you start up, I'll get them all. All right. So it turns out there are 4. All right. Let's see here. So first there's a direct path, which we don't include. But now, as you see, there's going to be backdoor paths because Waffle Houses don't affect anything else. They only have this direct effect possibly. And so what we see is that we have W is affected by S, and then that goes on to M, and that goes on to D. That path right there. We have W goes down to A and goes to D. we have W, S goes to M goes back from A, and then that goes to D. And then we finally have W, S, A, and then we go up to M, and then we go to D. So these are the 4 paths. Now the next step, which ones are open? All right, so let's look at it. All right, pause if you want to. So this is a fork right here. That one's open. And then you have a pipe. So it's a fork right there, and then it's a pipe. So yep, that one's open. Let's see here. How about this one? It's a fork and then a pipe again. That one's also open. You can imagine that if you change the value of being in the south, which is what this is, it changes how many Waffle Houses there are. Let's say it increases the number of Waffle Houses when you're in the south, but it also increases, say, the marriage rate, which increases the divorce rate. And so because of that, you might see that when the Waffle Houses are high, you see a high amount of divorce rate. But what you're actually picking up is that you're in the South, and that's increasing both the marriage rate and thus the divorce rate, and also simultaneously increasing the number of Waffle House restaurants. All right, here, let's see here. There's a fork. This right here, you can see when we go through here, this is a collider, right? So this one is not open because M right here is currently the collider, and that blocks it. And then right here you have S, that's just a long pipe, so that one's also open. So now what we gotta do is close these. So let's look at it. How do we close this one? We can close this one with either S or D, right? Maybe I'll label right here. S or D, both close, right? This one right here, S or A closes. This one is not currently open, so we don't have to worry about this one. Right now, this one, S closes it, A closes it, M closes. Once we close one of these, these are both pipes, and this one's a fork. Close any one of them, and the whole thing's closed. So we could say S or M or D. Sorry, S, A, or M. Right? So let's look at this. So one choice is for sure we can just close S, right? If we condition on S, so let's see here. One, we can just condition on S. And if we added an S into a regression, what that would do is it would close all the forks right here, this one fork. And with that, you break off Waffle House from any of the other effects. Cool. All right. Secondly, what else can we do? There's probably some other way. Well, let's see here. If we conditioned on, I'm sorry, did I say D here? I meant to say M for this one. I'm sorry. Obviously, you don't condition on D. That's the outcome. So S or M. So we could do S, and that'll work. This also seems to show that this one, if we close M, it works. This one, if we close M, it works. So this one, if we close A, it works. Same thing with this one. So what if we did both A and M? And M, right? Before we do that, actually, this is another solution, but just bear with me here. Suppose I had just closed A, right? That would close off this one and close off this one, but leave, and this one's already closed, but it would leave this one open, right? If I just closed M, what would happen? Now, this one's a little bit trickier. This one would close off, which is good because it closes that pipe. This one would stay open. This one would close because it closes this pipe. But by conditioning on M, this one actually opens up, right? Suddenly, this one will be an open up path, and now we'd be having a collider bias. So just doing M doesn't work. But if we do both A and M, now let's look at this. So this one closes because we condition on M. This one closes because we condition on A. This one closes doubly because we closed both of these. And what happens to this one? We got to check this one now. Because when we condition on M, this path becomes open. But because we also conditioned on A, it closes off that fork. And so while we open up this part, we close another door right here. And so the whole thing ends up being closed. So you can either do S or you can do A and M. And technically you do a combination of them too. That's also fine. All right. So those are actually the two ways that you do it. So you can do a regression where you do W on D and then you include just S, or W on D and you include both A and F. So one thing that you'll notice here, though, is if I wanted to say measure the effect of the South on divorce rate, I might include totally different variables than for the waffle on divorce. If I want to measure the effect of age on divorce rate, I might close totally different set. I might include different variables. All right. And so one thing that's interesting about this is that what variables you include in your regression depends on which arrow you're actually trying to measure. Right? If you want to measure a different arrow in the system, you might include totally different variables. All right. So I just want you to be aware of that. It's an interesting problem. All right. And so there is no just one correct regression. It depends on what you're trying to actually talk about. All right. So for the very last part of today's class, I just want to go over post-treatment bias very quickly. It's a really interesting problem. And all I have to do is just draw up a little diagram, and it should make complete sense on what's going on here and why it's so dangerous. This is another one where when you include a variable, you screw everything up. All right. So what happens is in the story that he has, and he generated some data with it, you have some plant, right? And the plant, you measure its height, and it's currently h0, right? H at height at time 0. And what you then later on, you measure its height at the end, right, of the time. And so you say, okay, well, clearly the height initially is going to help you predict or cause the final height, right? Because if you start off taller, maybe you grow less, or maybe you start shorter, than you grow more, or maybe it's less. Maybe you just innately have genes that make you tall for this plant, right? So if it's tall earlier, it's going to be even taller in the future. And for sure, it's probably not going to shrink in size. So it's going to be at least H0 plus some amount, right? So it's clearly, it helps you predict if you know the height. Secondly, though, there is a slight problem with the plant, which is that sometimes it can get fungus, right? And unfortunately, the fungus, if the plant gets the fungus, if that's a 1 and it has a fungus, it leads it to not really be able to grow as much. The fungus oftentimes, makes things not grow as well. So what we do, though, is we decide to run an experiment where we have a little spray or a different type of soil or something that helps fights against the fungus, right? So now we have some treatment T, which affects the fungus, and we want to say, hey, does the treatment work for increasing the height at the end of the day? So we collect our data on our initial heights and the final heights and the fungus and the treatment, and we want to measure it. Now, we'll generate the data real fast. I already have the code up, so don't worry, it'll go by really fast. Should be done within a few minutes. So here we go. This is how he did it. He first said, okay, the initial height is just some random value, 7 on 10. And then what happens is that half of the plants get the treatment, which is a 1 there, and the other half don't get it, and so it's 0. All right. Then to figure out how much fungus they have, you draw a random value where it's going to be you're going to flip a coin essentially, but the probability of getting the fungus is it's 50% minus the treatment times 0.4. So if treatment is 0, if you didn't get the treatment, then that whole term is 0, and you have a 50-50 chance of getting the fungus. If you do get the treatment, then that reduces it down to only a 10% chance of getting the fungus. And then finally, the final height is the initial height plus some random value it typically adds 5 extra to the height if it does not have a fungus, if the fungus is 0. And if it does have fungus, then it only adds 5 minus 3, which is 2. All right. So now you sit there and I'm not going to go through exactly how the model's set up, but it's a fairly straightforward model where you try to estimate the treatment, where you pass in all the variables, right, including the fungus, and you run it. and you find out that the effect that the treatment has, the beta for the treatment on the final height, is essentially 0. Our best guess is 0.03, and it ranges from minus 0.02 up to 0.08. It's pretty much 0. And of course, but luckily we do find that the effect that the fungus has is substantially negative. Not a surprise, right? Because clearly getting the fungus does lead to a reduction in height. Meanwhile, so what's happening here? Why aren't we picking up the treatment even though it clearly has an effect? Right? I mean, we have it right here. That is reducing the fungus, and we know the fungus reduces the height, so certainly the treatment is reducing the height. I mean, the treatment has an effect on the height, and getting the treatment increases your height because it reduces the amount of fungus you get. Well, the problem is that we've conditioned on fungus. We've included fungus in there. And so because this is a pipe, we close it off once we included fungus, right? Now what we're saying is, okay, conditional on having the fungus, for example, how much does the treatment affect your height? Well, none at all, because the only way that the treatment affects the height is by changing whether or not you have fungus. If you say, okay, well, you don't have fungus, look at all the ones that don't have fungus. Does the treatment affect height? No, it doesn't. Right? It doesn't do anything to the height except change whether or not you have fungus. So this is called post-treatment bias, where you have a treatment that's having an effect, but you close it off by including the way that it actually affects the value the outcome. So in this case, you absolutely do not want to include this. And what I said at the very beginning, if you're just worried about prediction, if you just want to predict the final height, then you want to include fungus because you just use the fungus to predict the final height and you don't care about the treatment variable, right? That's one step removed because sometimes you apply the treatment and it still gets the fungus, right? And sometimes you don't apply the treatment and it doesn't get fungus. So if you want to just predict the final height, you ignore the treatment and use fungus and H naught, right? And that will get you a really good prediction. But if you're interested in the effects, when you're interested in causal questions, such as does the treatment work, then you don't want to include fungus. And the problem is that no matter what type of method you use to try to figure out whether or not to include it, this is the only way to do it. It includes the information outside the data set. Because if you try to use stuff like out of sample performance, how well it fits the data, no matter what you do, including the fungus is going to look by any objective measure to help you better predict and better estimate H1. It'll look like the better model no matter what type of metric you use, except the metric of common sense. With here, you know when you're interested in the causal effect that you should not be including the fungus. All right. And this is something I've run into in my own experience where in one of my experiments, maybe I'll show you in class, I had some data with some auction stuff. And in one of the treatments, they would end up buying some more of a certain unit, and that would affect their profit in some way. But the treatment itself also had an effect on their profit, where something like treatment, and then their buying behavior, and then you had their profit. And what you might do by accident is control for their buying behavior here. And now you're closing off part of the effect that the treatment actually had on their profit. And so once again, it depends on whether or not you're interested in the direct effect or the overall effect. But if you include it, sometimes you could accidentally underestimate the effect of your treatment. And so this is something I actually ran into, and I had to be very careful to not, even though I was really tempted to just naturally, oh yeah, I got to toss this in and adjust for how much they're buying of this extra product. And it's like, no, don't include that. That's adjusting away a lot of the effect of the treatment. And so I had to leave that out. And like I said, I'll maybe show you that data. We'll at some point analyze that data, probably later in the semester. All right. That does it for today. That kind of covers just the very basics of causal analysis. There's a lot more to it. All right. There's things like regression discontinuities. There's instrumental variables. There's lots of various ways on do calculus. Not do calculus. Yeah, I think it's do calculus. Yeah. They get confused with lambda calculus for a second there. There's whole books on this stuff. And so one person that you can read if you're really interested in this stuff is Judea Pearl. He has a lot of books just dedicated to this. And I think right now he's trying to work on how to try to incorporate some causal analysis into machine learning. Another person who's really big in this is Donald Rubin. He's done a lot of stuff. He's a really pretty famous statistician. And so you can always read up on a lot of their stuff, and they help you try to get to some of this causal stuff. There's also propensity matching. There's a lot of kind of neat stuff that you can do with this. All right, but that does it for this week. All right, I'll see you guys later.